There is a sum you can do in your head tonight, with numbers you already know, and it will give you the wrong size of the universe. The universe is 13.8 billion years old. Light travels at a fixed speed, and nothing beats it. So the farthest thing we could ever see should sit 13.8 billion light years away, and the whole observable universe should be about 28 billion light years across. That answer feels airtight. It is also wrong by more than triple. The real distance to the edge, in every direction, is 46.5 billion light years, and the universe we can see is 93 billion light years across. The arithmetic was never the problem. Something was hiding inside an assumption we never thought to question, and finding it quietly rearranges everything you believe about how big reality actually is. Get comfortable. Hit subscribe if you're new here, because by the end of this, the night sky will stop being a picture of the present and become something far stranger. Now, let's slowly ease into this. Part 1. The number that should not be possible. There is a calculation you can do tonight, in your head, with numbers almost everyone already knows, and it will give you the wrong answer about the size of the universe. It will not feel wrong. It will feel like simple arithmetic, the kind no one could argue with. And the gap between the answer it gives you and the answer the universe actually holds is one of the strangest, most quietly unsettling facts in all of modern science. Here is the calculation. The universe is about 13.8 billion years old. We know this with real precision now. The best measurement from the Planck satellite puts it at 13.797 billion years, give or take a few million. Light, meanwhile, travels at a fixed and famous speed about 299,792 kilometers every second, and nothing carrying information can go faster. So, if light has been traveling toward us for 13.8 billion years, the farthest thing we could possibly see must be 13.8 billion light years away. The most distant edge of everything visible would sit at that distance in every direction, and the whole observable universe would be a sphere a little under 28 billion light years across. That is the answer that feels correct. It is also wrong, and not by a little. The observable universe is not 28 billion light years across. It is about 93 billion light years across. The edge in every direction is not 13.8 billion light years away. It is roughly 46.5 billion light years away. The universe is more than 3 times larger than the most natural calculation you could make, and the calculation was not the problem. Every number in it was right. The age was right. The speed of light was right. The multiplication was right. Something else was wrong, something hidden inside the assumption we never thought to question. I want you to sit with how odd this is for a moment, because it is easy to skate past. We are not talking about a rounding error or a fuzzy estimate at the ragged edge of knowledge. We are talking about light that has had 13.8 billion years to travel, arriving from a place that is now 46 billion light years away. The light covered far less distance than the distance to its source. It is as if you mailed a letter. It travelled for an hour at a steady walking pace, and when it arrived, the sender was somehow standing 3 times farther away than the total distance the letter had walked. On the face of it, that is impossible. The letter cannot reach you from farther than it travelled, and yet the universe does exactly this every night, with every photon that lands in every telescope on Earth. The resolution to this is not a trick of definitions, and it is not some asterisk that physicists added to cover an embarrassment. It is the central truth of cosmology, and once you understand it, the entire universe rearranges itself in your mind. But I am not going to hand it to you yet, because the answer only means something once you feel the size of the thing it is explaining. A number like 93 billion light years is just a string of words until you have climbed up to it, one rung at a time, from something you can actually picture. So before we explain why the universe is bigger than it has any right to be, we are going to find out exactly how big it is. We are going to start at a scale you know in your body, and we are going to climb until the climbing breaks something in your sense of what is real. And I want to plant one idea now, gently, because we will come back to it again and again, and it will mean more each time. The edge of the observable universe is not a wall. It is not a place where space stops and something else begins. There is no barrier out there, no surface you could press your hand against. The edge is a moment, not a wall. It marks the farthest that light has had time to reach us from, which means it is a boundary made of time, drawn around us by the age of the universe and the speed of light, and it is different for every observer who has ever lived or ever will. Hold on to that phrase. The edge is a moment, not a wall. By the end of this, it will have changed its meaning completely. It is worth pausing on why the wrong answer feels so unavoidable, because the feeling is the whole point. Our intuition about distance was built on a planet where the ground stays put. When you measure the length of a room, the room does not grow while your tape measure crosses it. When a car drives for an hour at a steady speed, the distance it covers and the distance to where it started are the same number, because the road is not stretching. Every instinct we have about space and travel was trained in a world of fixed distances, and that training works perfectly for rooms and roads and journeys across a continent. It only fails when the distances become large enough and the times long enough that the universe itself has a chance to change shape during the trip. On Earth, nothing is ever far enough or old enough for that to matter. In the cosmos, almost everything is. So the gap between the answer that feels right and the answer that is right is not a sign that you are bad at arithmetic. It is a sign that the universe operates on rules that never had a reason to show themselves in ordinary life. The people who first worked this out were not cleverer than you. They simply followed the measurements to a conclusion that contradicted their instincts and trusted the measurements anyway. That is the move we are going to make together. We are going to trust the climb, rung by rung, even when it carries us somewhere our instincts refuse to follow. Humans have been asking how big the sky is for as long as there have been humans to look up. For most of our history, the honest answer was that no one knew, and the guesses ranged from a dome a few miles overhead to a sphere of fixed stars not far beyond the planets. Every time we built a better instrument, the answer grew, and it grew by amounts that repeatedly humiliated the people doing the measuring. The universe has never once turned out to be smaller than expected. Every revision has been upward, often by factors of thousands or millions at a stroke. We are about to make that same journey in compressed form, and the destination is a number that, even now, with all our instruments, still does not quite fit inside the mind. So, let us begin where you are. Take a breath, settle in, and let us start the long climb out from here, because the only honest way to understand a number that should not be possible is to earn it. Part 2. Leaving home. Start with your own hand. Rest it somewhere in front of you and look at it. The width of your hand is something like 20 centimeters, a measurement so familiar your brain barely registers it as a measurement at all. This is the bottom rung of the ladder we are about to climb, and I want you to keep it in mind because the whole point of this journey is that every rung will make the rung below it look microscopic, and your hand will become, very quickly, a thing too small to find. Step out from your hand to the planet under you. The Earth is about 12,742 kilometers across. If you could drive in a straight line at highway speed without stopping, it would take you weeks to cross a single one of its oceans. From the window of the space station, the whole curve of the Earth fills the view, and astronauts describe the strange feeling of watching an entire continent slide past in minutes. This is the largest object most human beings will ever stand on, and on the ladder we are climbing, it is about to vanish beneath us. Now leave the Earth and reach for the Sun. The distance from the Earth to the Sun is what astronomers call 1 astronomical unit, about 149.6 million kilometers. That number is too large to feel, so let us translate it into something more honest. Light, the fastest thing there is, takes 8 minutes and 20 seconds to cross it. When you feel sunlight on your face, you are feeling light that left the sun more than 8 minutes ago. The sun you see is always the sun of 8 minutes in the past. If the sun simply vanished, you would have no warning, no flicker, nothing, for 8 full minutes, and then the light would run out and the sky would go dark. Already, at this very first step beyond our own planet, we have stumbled into the strange truth that will haunt this entire story. To look at something far away is to look at it as it was, not as it is. We will come back to this, because it gets much stranger. Keep moving outward. Past the Earth lie the other inner planets, then the Great Gap, then the outer giants. Neptune, the most distant major planet, orbits at about 30 astronomical units from the Sun. Light that crossed from the Sun to the Earth in 8 minutes takes more than 4 hours to reach Neptune, and Neptune is nowhere near the edge of the Sun's territory. Keep going, far past the planets, and you reach a place where the Sun's outward wind of particles finally loses its push against the thin gas of interstellar space. That boundary is called the heliopause, and it sits at roughly 120 astronomical units out. We know its distance for a reason that still gives me a chill. We have been there. The Voyager 1 spacecraft, launched in 1977, crossed the heliopause in 2012, at a distance of about 121 astronomical units, and became the first human-made object to leave the bubble of the Sun's influence and enter the space between the stars. It is still out there, still faintly calling home, its signal now taking more than a full day to reach us. And even Voyager, even after almost half a century of flight at over 60,000 kilometers per hour, has not truly left the solar system, because the Sun's gravity holds a final, faint dominion far beyond the heliopause. Surrounding everything, in a shell that may stretch out to 100,000 astronomical units, is the Oort cloud, a sparse halo of icy bodies that marks the true gravitational frontier of our star. 100,000 astronomical units is about 1.5 light years. To put that in plain terms, the outermost edge of our own solar system is so far away that light from the Sun takes 1.5 years to reach it. Voyager, our fastest ambassador, will not pass through the inner edge of the Oort cloud for another 300 years, and will not reach its outer edge for tens of thousands of years more. There is a model that astronomers use to teach this, and it helps to carry it with you. Shrink the Sun down to the size of a large grapefruit and set it on a table. On that scale, the Earth becomes a grain of sand about 15 meters away, a small room's width from the grapefruit. Jupiter, the largest planet, is a peppercorn some 80 meters off. Neptune, at the edge of the major planets, is another grain of sand more than 400 meters away, the better part of 0.5 kilometer from the grapefruit on the table. And the nearest star on this same scale, the next grapefruit, sits about 4,000 kilometers away, far enough that you would have to cross an ocean to reach it. That is the texture of the solar system and the space beyond it. A few tiny specks separated by enormous emptiness, and then nothing, for distances so large the model breaks down entirely. Hold on to what the Voyager mission actually represents inside that emptiness, because it is humbling. Voyager 1 carries a golden record, a phonograph disc engraved with sounds and images of Earth, sealed against the cold and the radiation, intended to last for hundreds of millions of years. It was a message in a bottle thrown into an ocean so large that the bottle will not reach the nearest far shore for tens of thousands of years, and even then only by accident, because it was not aimed at any star. The spacecraft is now so distant that its radio signal, travelling at the speed of light, takes more than 20 hours to reach us, and arrives so faint that receiving it at all is a feat of engineering. This is our farthest reach, the longest arm humanity has ever extended into the dark, and it has barely cleared the doorstep of our own star. The emptiness between the planets is itself worth feeling, because it is so unlike the crowded diagrams we grew up with. In a textbook, the planets are drawn close together, lined up like beads, because otherwise they would not fit on the page. The real solar system is almost entirely vacant space. If you were riding along with Voyager right now, you would see no planets nearby, no landmarks, nothing but the sun shrunk to a brilliant star behind you, and the true stars scattered ahead, unchanging for years at a time. Crossing the solar system is not like crossing a busy city. It is like crossing an empty plain at night, so large that the lights at its edges never seem to get any closer, for decades on end. It is worth converting these distances into the language of an ordinary road trip, just once, to feel how the human scale fails. If you could drive a car at highway speed, 100 kilometers per hour, without ever stopping, it would take you about 170 years to reach the sun. The same car would need around 4,000 years to reach the edge of the planets at Neptune, longer than all of recorded history, just to cross our own planetary system in a car. To reach the inner edge of the Oort cloud at that speed would take well over 1 million years, and to reach the nearest star, Proxima Centauri, the drive would last more than 45 million years, longer than the time since the dinosaurs vanished. These are the distances of our own immediate neighborhood, the cosmic equivalent of our front yard, and a car cannot cross them in the lifetime of a species. The reason we use light years and light minutes is not to sound grand. It is that ordinary units of human travel simply collapse under the weight of these numbers and stop meaning anything. And remember, as we leave the solar system behind, that everything we have described so far, every planet, every comet, the entire reach of the sun's gravity out to the Oort cloud, is the part of the universe we know best, the part we have actually sent machines into, the part that is in every sense our home. It is the rounding error. It is so small against what comes next that it will not even register on the scales we are about to use. We are about to leave the only neighborhood any human hand has ever touched, and we will not return to anything we could reach for the rest of this journey. Stop here and look back. We have not gone anywhere yet in cosmic terms. We have not even reached another star. We have simply walked out to the edge of our own sun's backyard, and already the distances have grown so large that our fastest machine, launched before most people listening were born, has barely begun the trip. Your hand is gone. The earth is gone. The sun is a brilliant point, and we are still, by every cosmic measure, exactly at home. The ladder has barely started, and the rungs are already pulling apart faster than the mind can follow. So let us take the next step, the one that finally carries us away from the sun entirely, out into the dark between the stars, where the real distances begin. Part 3. The dark between the stars. The nearest star to our sun is called Proxima Centauri, and it sits 4.2465 light-years away. Say that number slowly, because it hides something enormous. A light-year is the distance light travels in a year, and light, remember, crosses the entire span from the sun to the earth in 8 minutes. To travel for a full year at that speed, never slowing, never stopping, is to cover a distance so large that writing it in kilometers gives you a number with 13 digits. And Proxima Centauri is more than 4 of those away. It is the closest star there is, our next-door neighbor, and the gap to it is so wide that the light leaving it tonight will not arrive at your eye until you are 4 years older. This is the rung where the ladder changes character, and I want to be honest about how big the jump is. From the Earth to the edge of the Oort cloud, we crossed about 1.5 light-years, and that already took us beyond the reach of our fastest spacecraft for thousands of years. But the Oort cloud of our Sun very likely brushes up against the Oort cloud of Proxima Centauri's neighbours because the stars are so far apart that their faint outer shells are almost the only things filling the space between them. The space between stars is not a little wider than the solar system. It is overwhelmingly, almost entirely, empty. If you shrank the sun to the size of a grain of sand, the nearest other grain would be kilometers away, with nothing but darkness in between. That is the true texture of our galaxy. Not a crowded field of stars, but a few scattered grains of light, separated by oceans of nothing. Now hold that image of how far apart two neighboring stars are, and let it expand, because our galaxy, the Milky Way, is not made of 2 stars, or 10, or 1,000. It contains somewhere between 100 billion and 400 billion stars, each one separated from its neighbors by those same crossings of light years. And the whole disk of the galaxy, the great flattened wheel that holds all of them, is about 100,000 to 120,000 light years across. Light, leaving one edge of the Milky Way, would take 100,000 years to reach the other side. Our own species, in its recognizable modern form, is younger than that. A beam of light setting out across our galaxy when the first modern humans were learning to make tools would still be in transit today. We are not at the center of this wheel. The sun sits out in the suburbs, about 26,000 light-years from the galactic core, on a minor spiral arm, circling the center once every 200-some million years. The last time the sun was in this exact spot on its orbit, dinosaurs walked the Earth. We are not still. We are riding a carousel so large that one turn takes longer than the age of mammals. And every star you can see, with your naked eye, on the darkest night, is a member of this same galaxy, almost all of them within a few thousand light-years, a tiny local cluster of neighbors. The full sprawl of the Milky Way is something no human eye has ever taken in, because we are inside it, looking out through its dust at the faint band of light we named long before we understood what it was. Here, on this rung, the strange truth from the solar system returns with far more force. When you look at a star 1,000 light-years away, you are seeing light that left it 1,000 years ago. You are not seeing the star as it is. You are seeing the star as it was when empires that no longer exist were at their height. Some of the stars in the night sky have already died, collapsed, or exploded, and we have not yet received the news, because the light announcing their death is still crossing the gap toward us. The sky above you is not a picture of the present galaxy. It is a layered record of many different pasts, all arriving at once, sorted by distance. You are never, at any moment, looking at now. Remember that phrase too. You are never looking at now. It will return, and when it does, it will stop being a curiosity and start being something that aches. Let me put the gap to Proxima Centauri in terms of our fastest machine, because the number is hard to believe. Voyager 1 is moving at about 61,000 kilometers per hour, faster than any human has ever traveled. If Voyager were aimed straight at Proxima Centauri, which it is not, it would take roughly 73,000 years to get there. 73,000 years to reach the single nearest star at the fastest speed we have ever achieved. The whole of recorded human history, every empire, every invention, every life that has left a written trace, fits into the last 5,000 of those years. To cross to our nearest neighbor would take 14 times the span of all recorded history. And that is the closest star of all. The others are far worse. The space between the stars is not truly empty, but it is close. It holds a thin haze of gas and dust, on average about 1 atom per cubic centimeter, which is a vacuum far better than anything we can manufacture on Earth. Across light years, that thin haze adds up to enough material to dim and redden distant starlight, and it is the raw material from which new stars eventually form. But to a traveller, it would feel like absolute nothing, a crossing of pure dark in which the stars ahead never seem to brighten and the stars behind never seem to fade, for tens of thousands of years. This is the ordinary condition of our galaxy. The bright crowded star fields you see in photographs are an illusion of perspective, many separate stars at many different distances flattened onto one image. Spread them back out into 3 dimensions, and almost all of the galaxy is empty, dark, and still. The shape of the galaxy itself is worth picturing, because we so rarely get to see it from outside. The Milky Way is a flattened spiral, a disk with curving arms wrapped around a central bulge, with a fat swarm of older stars at its core, and a supermassive black hole, 4 million times the mass of the Sun, sitting at the very center. We cannot photograph the whole thing because we are embedded inside the disk, about 2/3 of the way out from the center. When you look up on a dark night and see the faint band of light that gives the galaxy its name, you are looking edge-on through the disk we live inside, seeing the combined glow of hundreds of billions of stars too far and too faint to resolve one by one. That pale band is our own galaxy, seen from within, and for most of human history no one knew that was what they were looking at. And the motion is relentless, even if we never feel it. The Sun, carrying the entire solar system with it, is sweeping around the galactic center at about 230 kilometers per second, which is more than 800,000 kilometers per hour. At that speed, it still takes between 2 and 250 million years to complete a single orbit. We have made this trip only about 20 times since the Sun was born. The galaxy turns so slowly, on such an enormous scale, that an entire human civilization is less than the blink of an eye against one rotation. And yet we are moving, always, faster than we can imagine, in a circle too large to perceive. And we are still only inside one galaxy. We have climbed from a hand to a planet to a star to 100 billion stars, and each rung has dwarfed the last, and we have not yet stepped outside the Milky Way even once. The next step does that. The next step leaves our galaxy entirely, and when it does, the Milky Way itself, this wheel, 100,000 light-years wide, becomes a single point of light among a crowd. So let us take it and watch our entire galaxy shrink to a smudge. Part 4. The Web That Holds Everything. Leave the Milky Way behind, and the first thing you find is that we are not alone out here, but our company is sparse and far away. Our galaxy belongs to a small gathering called the Local Group, a loose family of more than 50 galaxies spread across about 10 million light-years. Most of them are small, faint dwarf galaxies, but 2 large ones dominate, our own Milky Way and the Great Spiral of Andromeda, which lies about 2.5 million light-years away. Andromeda is the most distant thing the human eye can see without any instrument at all. On a truly dark night, it is a faint smudge in the constellation that bears its name, and the light forming that smudge left Andromeda 2.5 million years ago, before our own species existed. You are looking, with your bare eyes, at a moment older than humanity. Andromeda is also coming toward us. Most galaxies in the universe are rushing away, for reasons that will become the center of this entire story. But Andromeda is close enough that the local pull of gravity wins over the cosmic drift, and it is falling toward the Milky Way at over 100 kilometers per second. In about 4 billion years, the 2 great spirals will collide and merge into a single, larger galaxy. This is one of the few cosmic events that is genuinely in our future rather than our past, and we will return to it at the very end of this journey, because what that merged galaxy will see, looking out at the universe, turns out to be one of the most haunting ideas in all of cosmology. But the Local Group, with its 50-some galaxies across 10 million light-years, is itself only a small knot in something far larger. Galaxies do not float at random. They are gathered into clusters, and clusters into superclusters, and these are arranged along immense threads. Our Local Group sits near the outer edge of an enormous structure called the Laniakea supercluster, mapped in 2014, which stretches about 520 million light-years across and contains the mass of 100,000 trillion suns. On that map, the entire Milky Way is not even a dot. It is a single point of motion in one filament of one branch of a structure so large that light takes 500 million years to cross it. And Laniakea is one supercluster among countless others, because here we reach the largest pattern in the universe, the one that organizes everything else. If you could pull back far enough to see hundreds of millions of light-years at a glance, you would find that all the galaxies, all the clusters, all the superclusters are strung along a network of glowing filaments, sheets and threads of galaxies wrapped around enormous, nearly empty bubbles of darkness. The bubbles are called voids, and some of them are hundreds of millions of light-years wide with almost nothing inside. The whole arrangement is called the cosmic web, and it is, at the grandest scale, what the universe is shaped like. Not a scatter of stars, not a crowd of galaxies, but a frothy, foam-like structure of light wrapped around emptiness, the largest pattern that exists. I want to give you a moment to simply float here, because the climb has been steep and you have earned a breath. Imagine drifting slowly through the cosmic web, with luminous filaments of galaxies threading past you in every direction, each thread made of thousands of galaxies, each galaxy made of hundreds of billions of stars. Between the threads, the voids open like enormous rooms with no walls and no floor, darkness so complete and so large that a beam of light would take hundreds of millions of years to cross a single one. There is no sound here, no up or down, only this slow, shining architecture turning gently in the dark, patient and enormous, and almost entirely empty. This is the scale at which the universe finally shows its true design, and it is beautiful in a way that has nothing to do with us, a structure that was assembling itself for billions of years before there was anyone anywhere to see it. The name Laniakea was chosen with care, and it tells you something about how the people who map these structures feel about them. It comes from Hawaiian words meaning immense heaven, and it was given to our home supercluster in 2014 by a team that had finally traced the motions of thousands of galaxies precisely enough to see the larger structure they belong to. What they found was that galaxies across an enormous region, including our own, are all slowly flowing toward a common gravitational basin, like water finding the low point of a valley, and that this whole flowing region is a single connected structure. We did not know which supercluster we lived in until 12 years ago, because it is so large that seeing its shape required measuring the movement of galaxies across hundreds of millions of light years. Our cosmic address was rewritten within the lifetime of most people listening. The voids on the other side of this architecture are as astonishing as the filaments, in their own way, because they are so profoundly empty. The largest known voids are hundreds of millions of light years across, with almost no galaxies inside them at all. If you lived on a planet in the middle of one of the great voids, your night sky might be nearly black even with the best telescope, because the nearest galaxies would be so far away as to be all but invisible. There are regions of the universe where a thinking creature could grow up genuinely believing its own galaxy was alone in the cosmos, simply because everything else is too distant to see. The universe is not uniformly sprinkled with light. It is concentrated into the threads and starved in the hollows, and the hollows take up most of the volume. It helps to think of the whole arrangement as a foam, the kind you get when you whisk soap and water, except the bubbles are voids, hundreds of millions of light years wide, and the soapy films between them are sheets and filaments made of galaxies. The galaxies gather where the films meet, and the largest clusters sit where several films intersect at once, like the dense knots of foam where many bubbles press together. This pattern was not designed and not placed. It grew, over billions of years, from almost imperceptible ripples in the early universe, tiny regions that were very slightly denser than average, and whose extra gravity slowly pulled in more and more matter, while the emptier regions emptied further. The cosmic web is the frozen record of those first faint ripples, amplified by gravity across the entire age of the universe into the largest structure that exists. Now hold that image of the cosmic web, the filaments and the voids stretching as far as imagination can follow, and understand that we are about to take one final step on this ladder, the step that gathers all of it together. Everything we have climbed through, the solar system, the stars, the galaxy, the local group, Laniakea, the entire cosmic web, all of it sits inside one more sphere, the largest thing we can speak about at all. That sphere is the observable universe. And when we name its size, the number from the very beginning of this journey, the one that should not be possible, finally returns. So take one more breath in the quiet of the web, and let us pull back to see the whole of everything we are able to see. Part 5. 93 billion light-years. Pull back from the cosmic web until all of it, every filament and void, every supercluster, gathers into a single sphere of light, and you have arrived at the observable universe, the full extent of everything we are physically able to see. Its diameter is about 93 billion light-years. Its radius, the distance from us to the edge in any direction, is about 46.5 billion light-years. Inside that sphere, the best estimates suggest there are around 2 trillion galaxies, though a more recent measurement using the New Horizons spacecraft, far from the glare of the inner solar system, argues the true number may be closer to a few hundred billion. Either way, take the lower figure, hundreds of billions of galaxies, each one holding hundreds of billions of stars, and the total number of stars in the observable universe comes out somewhere around 10,000 billion. Written out, that is a 1 followed by 22 or more zeros. There are, by most estimates, more stars in the observable universe than there are grains of sand on every beach and in every desert on Earth. Let us make sure that number has actually landed, because it is easy to let it slide past, as just another large figure. We climbed, rung by rung, from your hand to this. Your hand was 20 centimeters. The Earth was a step up so large the hand vanished. The Sun was 8 light minutes away, and the Earth vanished. Proxima Centauri was 4 light-years away, and the whole solar system vanished. The Milky Way was 100,000 light-years across, and the gaps between stars vanished into it. Laniakea was 520 million light-years across, and the Milky Way became a point. And now the observable universe is 93 billion light-years across, and Laniakea itself, that structure light takes 500 million years to cross, is a single small fleck within it. Every rung made the one below it disappear, and we climbed at least 7 rungs, and the thing at the top is so much larger than the thing at the bottom that no human intuition can hold both ends at once. That is the true scale of the universe, or at least the true scale of the part we can see. But notice, now that we are standing at the top of the ladder, that the number we have arrived at is exactly the number that should not be possible, 46.5 billion light-years to the edge, and the universe is only 13.8 billion years old. We are right back where we started, except now we have felt the size of the thing, and the contradiction is no longer a piece of arithmetic on a page. It is the actual boundary of everything visible, sitting more than 3 times farther away than light could have travelled in the entire history of time. The light from the most distant galaxies took almost the whole age of the universe to reach us, and those galaxies are now nearly 50 billion light-years away. The light did not travel 50 billion light-years. It travelled, at most, about 13.8 billion years worth of distance. So how is the source now sitting so much farther out than the road the light ever covered? Pause on the climb itself for a moment, because the shape of it carries a lesson. At every single rung, the thing we thought was enormous turned out to be a speck against the next rung up. The Earth felt like the largest thing imaginable until the Sun made it a grain of sand. The solar system felt boundless until the gap to the nearest star swallowed it whole. The galaxy felt like everything until it became one point of light in the local group, and the local group became a fleck in Laniakea, and Laniakea became a smudge in the observable sphere. Not once did the next rung merely add a little. Every rung made the rung below it vanish. That pattern, repeated 7 or 8 times in a row, is the real shape of cosmic scale, and it is why no single mental image can ever hold the whole thing. The mind can grasp any one step. It cannot grasp all of them stacked together, because the top of the ladder is larger than the bottom by a factor with more than 20 zeros. There is one more thing to make clear before we resolve this, because it is the most common misunderstanding about the whole subject. When we say the observable universe is a sphere 93 billion light-years across, with us at the center, it sounds as though we occupy some special place, the middle of all creation. We do not. Every observer, anywhere in the universe, sits at the center of their own observable sphere, because their sphere is simply the region close enough that light has had time to reach them since the beginning. A civilization in one of those most distant galaxies would see their own 93 billion light-year sphere centered on themselves, and we would be the faint smudge at the edge of it, and to them we would be the ancient past. The observable universe is not a place with a center and a rim. It is a horizon that travels with each observer, a circle drawn around every set of eyes by the same 2 facts. The universe has a finite age, and light has a finite speed. The edge is a moment, not a wall, and that phrase is about to start paying off. Let me try to make the number of galaxies land in a different way, because 2 trillion, or even a few 100 billion, is just a sound until you give it a shape. Suppose you decided to visit every galaxy in the observable universe, and you could somehow tick one off every single second, day and night, without ever stopping to rest, 1 galaxy per second. Starting from a few 100 billion, it would take you more than 10,000 years just to count them, never mind visit them, and if the higher estimate of 2 trillion is right, more than 60,000 years. And each of those galaxies, ticked off in a single second, is itself a city of hundreds of billions of stars, most of them with planets, spread across 100,000 light-years. The counting exhausts a human lifetime many times over before you have even finished naming the islands, let alone exploring a single one. The fact that we sit at the center of our observable sphere deserves a little more attention because it is the source of one of the oldest mistakes in human thought. For most of history, people assumed that if the heavens appeared to surround us evenly, then we must occupy the middle of creation, a place of special importance. The expanding universe gives that appearance to everyone, everywhere, and means nothing of the kind. Picture an enormous loaf of raisin bread rising in an oven. Pick any raisin you like, and from that raisin's point of view, every other raisin is moving away from it, and the ones farthest away are receding fastest, and it looks for all the world as though that raisin is the center of the expansion. But every raisin sees exactly the same thing. There is no central raisin. The bread is expanding everywhere at once, and the appearance of being at the center is an illusion shared by every point inside it. We are at the center of our observable universe in precisely that way, which is to say, not specially at all. This also means there is almost certainly far more universe than the part we can see. The observable universe is simply the region close enough that its light has reached us in the time available. Beyond our horizon, the universe continues, very likely looking much the same, full of galaxies and superclusters and cosmic web, stretching on past the limit of our sight. How far it continues, we do not know. The honest measurements tell us that on the largest scales, the universe is geometrically flat as we can measure, and a flat universe may well be infinite, with no edge and no end anywhere. The 93 billion light-years is not the size of the universe. It is the size of the portion we are able to observe, a bubble of visibility inside something that may have no boundary at all. We have climbed to the top of the ladder we can climb, and discovered that the ladder simply continues up past the highest rung we can reach. So we have climbed the whole ladder and arrived at the top, at a genuine impossibility, a source of light that is now farther away than the distance its light ever travelled. The number is real, the contradiction is real, and the only way out of it is to give up an assumption we have been making silently this entire time, an assumption so natural that we never noticed we were making it. We have been assuming that space itself stays still while light moves across it. We have been assuming that the distance between two things is a fixed stage on which light runs its race. That assumption is wrong, and abandoning it is the single idea that explains everything. So let us abandon it now and watch the impossible become inevitable. Part 6. The ruler that stretched. Here is the assumption we have to drop. We have been picturing space as a fixed background, like the floor of an enormous room with galaxies sitting on it and light running across it. In that picture, the distance light travels and the distance to its source are obviously the same, because the floor never changes. But the floor does change. Space itself is expanding. The distances between galaxies are not fixed. They grow with time, everywhere, all at once. And this single fact dissolves the entire paradox, because if the floor itself is stretching while light crosses it, then the source can end up far more distant than the road the light ever travelled. Let me make this physical, because it is too important to leave abstract. Imagine a single particle of light, a photon, leaving a young galaxy not long after the universe began. It sets out across the dark, heading toward the patch of space where, billions of years later, the Earth will eventually form. The photon moves at the speed of light, the fastest anything can go, and it never slows down. But as it travels, the space in front of it is lengthening. Every stretch of distance it has already crossed is also lengthening behind it, pushing its origin galaxy farther and farther away, even as the photon races forward. The photon is like a swimmer setting out across a lake whose far shore keeps drifting backward, while the water it has already swum through keeps swelling. The swimmer never stops, never tires, but the lake is growing under and around it the entire time. Travel with that photon for a moment. It is moving as fast as the universe permits, pouring straight ahead through the dark, and yet the destination keeps receding, so the journey takes far longer than the original distance would suggest. 13 billion years pass. The photon has never once slowed, and when it finally arrives, falling into a telescope mirror on Earth, the galaxy that released it is no longer where it was. The space between has stretched so enormously that the source now sits 46 billion light-years away, even though the photon only ever experienced about 13 billion years of flight. The light did not break any rule. It travelled for 13 billion years at exactly the speed of light. It is the ground beneath it that changed. The ruler we measure with, the fabric of space itself, grew longer while the light was in motion, and that is the whole secret. That is why the universe is bigger than its age, times the speed of light. The age times the speed of light tells you how far the light travelled. It does not tell you how far away the source has since been carried, because the source has been riding the expansion the entire time. Stay with that photon a moment longer, because its journey is stranger than any voyage we could design. It does not experience the trip the way a traveller would. From the photon's own frame, in a sense, no time passes at all. But from our frame, watching it cross the expanding universe, it spends billions of years in flight, and the universe it passes through is never the same universe twice. It leaves a young cosmos, crowded with newborn galaxies blazing with the first generations of stars, and it arrives in an older, cooler, more spread out cosmos, where those same galaxies have aged and drifted apart. The space it travels through is quietly lengthening beneath it the entire way, so that the simple straight line it follows is, in truth, a line that keeps getting longer even as the photon advances along it. The light is not just crossing a distance. It is crossing a distance that is being manufactured around it, and the final separation between us and its origin is the sum of everything it crossed, plus everything that was added behind it while it crossed. This is the precise reason the size paradox dissolves, and it is worth saying it once more in the plainest possible words, because everything else in this story hangs on it. The age of the universe times the speed of light tells you how long the light was traveling and how far it would have gotten across a fixed, unchanging space. But space was not fixed and not unchanging. While the light traveled, the space behind it kept growing, pushing its source farther and farther back, so that by the time the light arrives, the source is much more distant than the road the light actually covered. The light traveled 13 billion years. The source is 46 billion light-years away. Both numbers are correct, and the gap between them is exactly the amount of new space that was created during the journey. The universe is bigger than its age allows, because the universe has been busy making more of itself the whole time. There is a fingerprint of this stretching written into the light itself, and we can read it. As space expands, it does not only carry galaxies apart, it stretches the light traveling through it. A wave of light, caught in expanding space, has its wavelength pulled longer, shifted toward the red end of the spectrum, and the farther the light has come, the more it has been stretched. We call this redshift, and it is the single most important measurement in cosmology. When we look at a distant galaxy and find its light stretched and reddened, we are reading, directly, how much the universe has expanded since that light set out. The most distant galaxies have their light stretched so severely that what began as brilliant ultraviolet arrives as faint infrared. The light has not lost energy to friction or grown tired on the road. It has been stretched by the growth of space itself, and the amount of stretch is a measuring tape laid across cosmic time. Notice what this does to the impossibility we started with. It does not explain it away with a technicality. It tells us the universe is even stranger and grander than the simple picture allowed. Space is not a stage. Space is a participant. It carries things. It stretches light. It grows. The reason the observable universe is 93 billion light-years across, rather than 28, is not that anything moved faster than light. Nothing did. It is that the space between us and everything else has been quietly, relentlessly enlarging for 13.8 billion years, and it is enlarging still, right now, as you listen, between you and every distant galaxy in the sky. It helps to know that this is not a recent or shaky idea, but one of the most solidly established facts in all of science, and that we can name the moment it was discovered. In 1929, an astronomer named Edwin Hubble, working at the Mount Wilson Observatory, compared the distances of galaxies with the redshift of their light and found a clean relationship. The farther away a galaxy was, the faster it appeared to be receding. This was the first direct evidence that the universe is expanding, that the galaxies are not fixed in place, but are being carried apart, and that the whole cosmos was smaller in the past. It is among the most important discoveries ever made, because it told us, for the first time, that the universe has a history, that it was once compressed and has been growing ever since. Everything we have said about the size paradox flows from that single relationship between distance and redshift. The word expansion can be misleading, so let me be precise about what is and is not happening. The universe is not expanding into anything. There is no outside, no empty room that the cosmos is growing to fill. The expansion is not like an explosion hurling debris outward through a pre-existing space, with a center and an edge and an outside. It is the distances inside the universe all increasing together, everywhere at once, with no center to the growth and no boundary it is pushing against. This is what physicists mean by the metric of space expanding. The metric is just the rule that tells you the distance between any 2 points, and that rule is changing with time so that every distance gets larger. Nothing is flying apart through space. Space is the thing that is growing, and it is growing from within, not into anything. And the expansion does not pull apart the things that are bound together by their own forces. Your body is not expanding. The Earth is not expanding. The solar system, the Milky Way, even the local group of galaxies held together by gravity, none of these are growing, because within them, the local forces, gravity and the forces that hold matter together, are far stronger than the gentle stretch of cosmic expansion. The expansion only wins out across the enormous distances between galaxies that are not gravitationally bound to one another, where there is nothing holding them together against the steady creation of new space. So the stretching is real and relentless, but it acts only on the largest, emptiest scales. On every scale you can touch, the universe is perfectly, reassuringly stable. The growth happens far away, in the gaps between island galaxies, where nothing is holding the distance fixed. And this raises a question that sounds like it should break physics in half. If space is carrying distant galaxies away from us, and it has carried some of them to a distance of 46 billion light-years in only 13.8 billion years, then those galaxies must be moving away from us faster than light. That seems to violate the one rule everyone knows, the cosmic speed limit, the law that nothing can outrun light. So either the rule is wrong, or something subtle is going on that lets the universe do what no object inside it is allowed to do. The answer is the second one, and understanding it is the next step, because it reveals that the speed limit you were taught is not quite the speed limit the universe actually enforces. Part 7. Faster than light, without breaking the law. Let us state the apparent crime plainly. The most distant galaxies we can see are receding from us faster than the speed of light. Not close to it, faster than it. The space between us and them is stretching so quickly that the gap widens at a rate no beam of light could ever match. And the famous law of physics, the one Einstein gave us, says nothing can travel faster than light. So it looks as though the universe is breaking its own most sacred rule, openly, in plain view, in every faint image of the distant sky. This is the point where many people conclude that something must be wrong, that the whole picture of an expanding universe must be a mistake, or that some truth is being hidden. But nothing is wrong, and nothing is hidden. The resolution is precise and beautiful, and it comes down to a single distinction. The cosmic speed limit forbids any object from moving through space faster than light. It says that here, locally, if you and I are standing in the same patch of space, you cannot fly past me faster than a light beam. That law is ironclad and has never been violated. But the recession of distant galaxies is not movement through space. The galaxies are not flying away from us across a fixed background. They are sitting more or less still in their own patch of space, just as we are sitting still in ours. What is growing is the space in between. New distance is being created everywhere, continuously, and when you add up all that new distance across billions of light-years of separation, the total gap can widen faster than light, even though nothing is actually traveling through space at all. The speed limit applies to motion across space. It says nothing about how fast space itself can stretch, because the stretching of space carries no object, transmits no signal, and breaks no causal law. This is the difference between a runner and a road. The cosmic speed limit governs the runners, the objects moving through the world. It has nothing to say about the road, which can lengthen as fast as it likes, because lengthening the road is not running on it. Distant galaxies are runners standing still on a road that is being stretched out from underneath everyone all at once. They are not sprinting away from us. The distance between us is simply being manufactured mile after mile, faster than light could cross it, and no law objects, because no thing is moving faster than light. The only thing exceeding the speed of light is the growth of empty distance. An empty distance is allowed to do anything. Now here is the part that genuinely bends the mind, the part that surprises even people who have made peace with everything so far. There is a distance, called the Hubble radius, at which the recession rate exactly equals the speed of light. With the expansion rate we measure today, that distance is about 14.5 billion light-years. You might think that everything beyond it, everything receding faster than light, must be invisible to us, forever cut off, its light unable to make headway against the stretching. And yet we see galaxies far beyond the Hubble radius. We photograph them routinely. Their light reaches us, even though, at the moment they emitted it, they were already receding faster than light, and even though they still are. How can light from a galaxy that is running away faster than light ever possibly reach us? The answer is that the photon does not have to win the whole race at once. A photon emitted toward us from a galaxy beyond the Hubble radius is, at first, actually losing ground. The space between it and us is stretching faster than the photon can advance, so, for a long time, the photon drifts farther from us in absolute distance, even as it points straight at us. But the expansion rate is not constant. In most of cosmic history, the rate at which a given distance recedes has been slowing, so the Hubble radius itself grows over time and reaches outward. Eventually, it can sweep past the struggling photon, and once the photon finds itself inside a region receding slower than light, it begins, at last, to make real progress toward us, and after billions of years it arrives. So the light we see from the most distant galaxies is light that spent ages swimming upstream against the expansion before finally breaking through. We are seeing photons that nearly did not make it, that hung almost motionless in stretching space for eons before the tide turned. The fact that we can see anything receding faster than light is not a contradiction. It is a record of an almost impossibly patient journey. There is a measurement that lets us read all of this directly, and it is worth knowing the name of it, because it turns these ideas from a story into a number we can check. That measurement is redshift, and astronomers label it with the letter Z. A redshift of 1 means the wavelength of the light has been doubled by the expansion, stretched to twice its original length, which means the universe has roughly doubled in size since that light was emitted. A redshift of 2 means the light has been stretched to 3 times its original wavelength. The Hubble sphere, the distance at which recession reaches the speed of light, corresponds to a redshift of around 1.5. So every galaxy we observe with a redshift greater than about 1.5 was already receding faster than light. At the moment it sent us the light we now see, and yet there they are, photographed and catalogued, thousands upon thousands of them. The faster-than-light galaxies are not exotic and rare. They are most of the galaxies in any sufficiently long exposure of the sky. The patience of the light that reaches us from those galaxies is genuinely moving once you understand it. A photon leaving a galaxy beyond the Hubble sphere, aimed straight at us, begins its life losing the race. For the first stretch of its journey, the space between it and us grows faster than the photon can cross it. So even though the photon is pointed directly at us and moving at the speed of light, the actual distance between us and the photon increases. It is running toward us and falling behind at the same time. Only because the expansion rate was decreasing for most of cosmic history did the situation slowly change, the region of faster-than-light recession contracting around us until the struggling photon finally found itself in space that was receding slower than light, at which point it began, at last, to make real headway and close the gap. The light we receive from the most distant galaxies spent billions of years almost stranded, hanging in stretching space, advancing by the thinnest of margins before the tide finally turned in its favor. Every faint smudge in a long exposure is a photon that nearly never made it. People sometimes hear all of this and suspect a trick, a loophole physicists invented to save a failing theory. It is the opposite. The distinction between motion through space and the stretching of space is not a patch applied after the fact. It falls directly out of Einstein's theory of general relativity, the same theory that predicts how gravity bends light and how clocks slow near massive objects, the theory that has passed every experimental test we have ever devised. The expanding universe was not assumed. It was predicted by the equations and then confirmed by observation. The faster-than-light recession is not a paradox the theory struggles with. It is a clean and unambiguous consequence. The theory hands you the moment you write down an expanding space. The universe really does behave this way, and the mathematics describing it is over a century old and has never failed a test. So the universe is larger than its age allows, because space stretches, and it can carry galaxies away faster than light, because stretching is not motion, and we can still see those galaxies because light is patient and the expansion was once slowing. Every piece fits. But all of this has a consequence we have been circling since the very first step beyond the Earth, a consequence about time rather than distance. Because if the light from the farthest galaxies took almost the whole age of the universe to reach us, then we are not seeing those galaxies as they are. We are seeing them as they were when the universe was young. And that means the sky above you is not a place. It is a time machine, and it only ever shows you the past. Part 8. The Museum of Light. Go back to the very first surprise on this journey, the one we found before we had even left the solar system. The sun you see is the sun of 8 minutes ago. That was charming when it was just our own star, but carry it all the way up the ladder we climbed, and it stops being charming and becomes something closer to vertigo, because every single thing you see in the sky, without exception, is the past. The light from Proxima Centauri shows it as it was 4 years ago. The light from the center of our galaxy left 26,000 years ago. The smudge of Andromeda is 2.5 million years old. And the most distant galaxies in the deepest images show the universe as it was more than 13 billion years ago, when it was a small fraction of its current age. You are never looking at now. You never have been. There is no instrument, no technique, no vantage point anywhere in physics that can show you the universe as it is in this instant, because the information simply has not arrived and never can all at once. This means the night sky is not a snapshot. It is a museum, and every exhibit is from a different era, all hung on the same wall, sorted by how far the light had to travel. When you look up, the nearby stars are showing you recent centuries. The farther stars are showing you the distant past of our galaxy. And if you had a powerful enough telescope, the most distant galaxies would be showing you the infancy of the cosmos. You are looking, simultaneously, at 1,000 different ages of the universe, layered on top of one another by distance. The sky is the only museum in existence, where the farther you look across the room, the older the artwork becomes, and where you can see, in a single glance, exhibits separated by more than 13 billion years. Now let the full weight of that settle, because it is heavier than it first appears. When you look at a long-exposure image, one of those photographs, where every speck of light is an entire galaxy, you are not looking at galaxies that exist out there right now, waiting for us. You are looking at galaxies as they were billions of years ago. In the billions of years since that light left them, those galaxies have lived entire histories. They have spun, formed new stars, merged with neighbors, aged. Some of them have been transformed beyond recognition. Some of them, in the time it took their light to cross to us, have likely been torn apart or burned out. The galaxy in the photograph is not a place you could visit and find unchanged. It is a portrait of something that has long since become something else, or ceased to be what it was. You are not seeing the universe. You are seeing its photographs, and every photograph is older than the last, and many of them are pictures of things that are, by now, gone. And this is true not only of impossibly distant galaxies, but of the ordinary stars you can step outside and see tonight. Some of the points of light scattered across your sky are stars that have already died, that collapsed or exploded centuries or millennia ago, and whose final light is still arriving, still crossing the gap, so that they go on shining in our sky as though nothing has happened. You could be looking, right now, at a star that no longer exists, and you would have no way to know. The sky keeps its dead lit. It cannot do otherwise, because the news of any death travels at the speed of light, and the speed of light, across these distances, is achingly slow. We live permanently inside an arriving past, surrounded by the lingering light of things we cannot know are still there. There is something almost tender in this. Once the vertigo passes, the universe does not let anything fully vanish. The light of every star that ever shone keeps travelling outward forever, so that somewhere, always, that star is still rising in someone's sky, still young, still burning, its light not yet arrived. Distance preserves the past the way amber preserves an insect, holding it perfectly, indefinitely, simply because the light needs so long to cross the gap. To look out into space is to walk through a hall of preserved moments, and to understand that we ourselves are an exhibit in someone else's hall, our own light streaming outward right now, so that in galaxies we will never reach, our present is being saved as a future they have not yet received. Take a single example you can step outside and find. The star Betelgeuse, the bright reddish point on the shoulder of the constellation Orion, sits something like 650 light-years away. It is a red supergiant near the end of its life, and astronomers expect it to explode as a supernova sometime in the next 100,000 years. Here is the strange part. Because its light takes about 650 years to reach us, the Betelgeuse we see tonight is the Betelgeuse of 6 centuries ago. It is entirely possible that Betelgeuse has already exploded, that the supernova has already happened, and that the light of that explosion is right now somewhere out in space, crossing the gap toward Earth. Not yet arrived. We could look up at Orion's shoulder and see a calm red star that in truth no longer exists, and we would have no way to know until the light of its death finally reached us, possibly tomorrow, possibly centuries from now. The sky shows us a past we cannot update on demand. This turns the simple act of looking up into something closer to reading old letters from people who may no longer be alive. Every star is sending us a report of how it was, stamped with the date the light departed, and we read all the reports at once, with no way to ask any of them for an update. The brighter, nearer stars send recent news. The fainter, farther ones send news from centuries or millennia ago. And the galaxies send news from before there was anyone to receive it. We are the recipients of a correspondence that spans the entire history of the universe, and the letters keep arriving, in order of distance, forever. There is a way to turn the museum around and point it at ourselves, and it is worth doing because it makes the whole idea personal. Right now, at this very moment, light is leaving you. Light is bouncing off your face, off the room you are in, off the whole surface of the earth, and streaming outward into space at the speed of light. That light will reach the moon in a little over a second, the nearest stars in a few years, and the nearest galaxies in millions of years. It does not stop. It keeps going, carrying an image of this exact moment outward forever. So somewhere, always, in galaxies we will never reach, this moment of your life is a future event that has not yet arrived. You are an exhibit in someone else's museum, your present preserved in light and travelling outward, to be received somewhere long after you are gone. The preservation runs both ways. Everything that has ever shed light is still shining somewhere, including you. But I have been gentle with you, and there is a harder turn coming. So far, the Museum of Light has been a place of preservation, where nothing is ever truly lost. That is about to change. Because the same expansion that made the universe larger than its age, the same stretching that carries galaxies away faster than light, is doing something else, something quieter and far more final. It is not only enlarging the universe we can see, it is beginning to take parts of it away from us, permanently, beyond any hope of return. And to understand why the universe keeps getting larger, we first have to understand the strange and unsettling sense in which it is also, at the same time, getting smaller. That is where we go next. Part 9. The Wall of Oldest Light. We have been climbing outward in distance, which means climbing backward in time, and you might think this can go on without end, that with a good enough telescope we could see all the way back to the very beginning. But it cannot go on without end. There is a limit, a farthest distance, an oldest light, and it forms a kind of wall around the entire observable universe. That wall is the cosmic microwave background, and it is the single most important thing we have ever detected, because it is a photograph of the universe as a newborn, the oldest light there is or ever can be. To understand the wall, you have to know what the early universe was like. For the first roughly 380,000 years after the beginning, the universe was so hot and so dense that ordinary atoms could not hold together. Electrons flew free, unbound, and a fog of these loose charged particles filled all of space. Light cannot travel far through such a fog. Every photon was absorbed and scattered almost the instant it was emitted, the way light cannot cross a thick bank of cloud. The early universe was opaque, glowing, impenetrable, a furnace with no clear line of sight. Then, as the universe expanded, it cooled, and at about 380,000 years, the temperature dropped just low enough for electrons to settle onto nuclei and form the first stable atoms. The fog cleared. All at once, across all of space, light was suddenly free to travel in straight lines, and it has been travelling ever since. That moment, when the fog lifted and light broke free, is called the surface of last scattering, and the light released then is what we now detect as the cosmic microwave background. It is the farthest thing we can see with light of any kind, because there is nothing visible behind it. Behind it is only the fog, opaque and impenetrable. When we look out to that wall, we are looking 13.8 billion years into the past, to within 380,000 years of the beginning itself, seeing the actual glow of the infant universe. And here is the part that makes it tangible. That light was originally a fierce glow, the radiation of a furnace at thousands of degrees. But the expansion of the universe has stretched it, redshifted it, the same stretching we have been talking about all along, except applied for the entire age of the cosmos. It has stretched the light by a factor of about 1100, pulling its wavelength from a brilliant glow all the way down to faint microwaves, and cooling it to a temperature of just 2.725 degrees above absolute zero. Follow one of those photons, the way we followed the light from the distant galaxy. It is born in the instant the fog clears, 380,000 years into the life of the universe, set loose at last as a vivid orange glow. It begins to travel, and it travels for 13.8 billion years. Around it, the universe darkens and cools and opens out. Galaxies form, live, and drift apart. The space it moves through stretches and stretches, and its own wavelength stretches with it, sliding down from orange to red to infrared and finally into the microwave, its colour draining away as the eons pass. It crosses almost the entire history of the universe untouched, a single particle of the primordial fire, until at last it falls into a radio antenna on a small planet and registers as the faintest possible whisper of warmth, a hiss in the receiver, the touch of the oldest light there is. When you tune an old television between channels, A small fraction of the static you see is exactly this, the relic glow of the newborn universe, arriving in your living room after a journey of 13.8 billion years. I want you to rest in this for a moment, because it is one of the strangest and most peaceful facts in all of science. This ancient light does not come from one direction. It comes from every direction at once, because the fog that released it filled all of space. It is everywhere, all around you, all the time, a faint warmth soaking through the room you are in right now, passing through your body, through the walls, through the planet, a tide of light from the dawn of everything with no single source and no single direction, simply present, everywhere, always. You are bathed in the afterglow of the beginning, gently, constantly, and you have never felt it, because it is so faint and so cold. But it is here, and it is the oldest thing you will ever encounter. The way we discovered this ancient light is one of the great accidents in the history of science, and it is worth telling because it grounds something so cosmic in something almost comic. In 1964, two radio engineers named Arno Penzias and Robert Wilson were working with a large horn-shaped antenna in New Jersey, trying to make careful radio measurements, and they kept finding a faint hiss of noise that they could not get rid of. It came from every direction in the sky, day and night, in all seasons. They checked their equipment exhaustively. They even found that pigeons had been roosting in the antenna and cleaned out the droppings, suspecting that might be the cause. Nothing they did removed the hiss. It turned out they had accidentally detected the cosmic microwave background, the relic glow of the newborn universe, without setting out to look for it. They received the Nobel Prize for stumbling onto the oldest light there is, while trying to eliminate it as static. The afterglow of creation first reached us, in a form we understood as an annoying noise two engineers were trying to silence. It is worth being clear about why this wall exists and what kind of wall it is, because it is not a wall of matter. The early universe was filled with a glowing plasma, a fog of free electrons and bare nuclei, and light cannot travel far through such a fog because the free electrons scatter it constantly, the way a flashlight beam cannot penetrate thick mist. For 380,000 years, the whole universe was this glowing, opaque mist. Then it cooled enough for the electrons to combine with nuclei into neutral atoms, the mist cleared, and light could finally fly free. So when we look out to the cosmic microwave background, we are not looking at a surface in the ordinary sense. We are looking at the moment the fog lifted, the last instant before the universe became transparent, seen from 13.8 billion years away, in every direction. It is a wall made of an event, the event of the universe clearing, and it surrounds us, because that event happened everywhere at once. The natural question is what lies behind the wall, and the honest answer is that there is more universe there. We simply cannot see it with light. Before the fog cleared, the universe was opaque to light, and no telescope of any power will ever see a photon from earlier than that moment, because no photon could travel freely back then. But light is not the only messenger. There are, in principle, two ways to see past the wall. The first is the cosmic neutrino background, a sea of ghostly particles released about 1 second after the beginning, far earlier than the light, which is passing through everything constantly, but is fiendishly hard to detect. The second is primordial gravitational waves, ripples in space itself that may have been generated in the first fraction of a second, which would carry information from earlier than any light could. We have not captured either of these relics from the beginning yet, but they are out there, in principle detectable, a way to one day see behind the wall of light to the genuinely first moments. The wall is the edge of what light can show us, not the edge of what exists, and not even, perhaps, the edge of what we will someday be able to study. Now return to the phrase I asked you to hold at the very beginning. The edge is a moment, not a wall. The cosmic microwave background looks like a wall, the farthest boundary of everything visible. But it is not made of stone or matter. It is made of time. It is the moment the fog cleared, seen from 13.8 billion years away. And it is not the edge of the universe. It is only the edge of what we can see. Beyond it, there is more universe, the same as ours, full of galaxies, where observers would see their own microwave wall in every direction, including ours. The wall is a horizon, the line past which light has not had time to reach us, and like every horizon, it is not a place you could ever arrive at. It recedes. It belongs to us, drawn by our particular position in time. The edge is a moment, not a wall, and now you can feel exactly what that means. The boundary of the visible universe is not the boundary of the universe. It is the boundary of how far back we are able to look. So we have reached the farthest light and found that it too is a horizon rather than a barrier. And that word, horizon, is the key to the question we have been postponing since the title of this whole journey. Why does the universe keep getting larger? A horizon, after all, is not a fixed line. It is the sort of thing that can move. And the horizons of the universe are moving in more than one way at once, which is exactly why the size of everything we can see is not a fixed number, but a changing one. Part 10. Why it keeps getting larger. The universe keeps getting larger in two distinct senses, and it is worth separating them carefully, because they are different and both are true. The first sense is the one we have already met. Every distance in the universe is physically growing. The space between us and every distant galaxy is stretching continuously, so the proper distance to those galaxies is larger today than it was yesterday and will be larger still tomorrow. The galaxy whose light shows it 46 billion light-years away is, even as we watch, being carried farther out. In this sense, the universe is getting larger the way bread dough rises, every part moving away from every other part, the whole thing swelling with time. Nothing is moving through space to make this happen. Space itself is simply growing, and so every measured distance grows along with it. The second sense is subtler and, in some ways, stranger. The observable universe itself, the sphere of everything we can see, also grows, because as time passes, light from regions that were previously too far away finally has time to reach us for the first time. Every year, the universe ages by a year, and that means light gets one more year to travel, and a thin new shell of previously unseen space crosses the threshold into visibility. Galaxies whose light had not yet arrived begin to arrive. The horizon, the moment not a wall we just described, creeps outward, and the volume of the universe available to our telescopes increases. In this sense, the universe keeps getting larger simply because it keeps getting older, and an older universe has had more time for distant light to complete its journey. It helps to picture these two kinds of growth as two different motions happening at once. Imagine the observable universe as a balloon being inflated, with galaxies painted on its surface. The first kind of growth is the painted galaxies drifting apart as the rubber stretches, every painted dot moving away from every other, which is the increase of every distance. The second kind of growth is harder to picture, but just as real. As time passes, you are able to see more of the balloon's surface than before, because light from farther around the curve has finally had time to reach your eye. So the patch you can see is both stretching and widening, the dots spreading apart while new dots come into view around the edge. Both are happening together, and both make the universe you can observe larger with every passing year. So the honest answer to the question this whole journey is built around how big is the universe and why does it keep getting larger has two layers. It keeps getting larger because space itself is stretching, so every distance between unbound galaxies grows without anything moving through space. And it keeps getting larger because the universe keeps aging, so light from regions that were once too far away keeps arriving for the first time, widening the sphere of everything we can see. Neither of these is a figure of speech. Both are measured, both are ongoing, and both are happening in the sky above you tonight, silently, as the distance to every far galaxy creeps upward and the faint light of regions never before seen completes its long arrival. These two growths together are why the answer to how big is the universe is not a single fixed number, but a quantity that has been increasing throughout cosmic history. When the universe was young, the observable region was tiny, because light had only had a little while to travel. As the universe aged, the observable region swelled, both because light had more time to arrive and because every distance within it was stretching. The 93 billion light-years we measure today is a snapshot of an ongoing process, the current reading on a dial that has been climbing since the beginning. If you had asked the question 1 billion years ago, the number would have been smaller. If anyone is left to ask it 1 billion years from now, the number, by some measures, will be larger. The universe is not a finished object of a fixed size. It is a growing one, and we are seeing it at one particular moment in its expansion. But I have to be careful and honest here, because there is a limit to one of these growths, and the limit is the doorway to the hardest and most beautiful part of this whole story. The second kind of growth, the steady arrival of new light from farther and farther away, would continue without end if the universe expanded in the gentle, slowing way that everyone assumed for most of the 20th century. In a universe whose expansion is gradually slowing under its own gravity, more and more of the cosmos would keep swimming into view forever, and given enough time, we would eventually see almost everything. For decades, that was the picture, a universe slowly applying its own brakes, with the only question being whether it would coast forever or someday recollapse. That picture was overturned, and the overturning is one of the most important discoveries in the history of science. In the late 1990s, two teams of astronomers set out to measure how fast the expansion of the universe was slowing down. They studied distant exploding stars, a particular kind of supernova that always shines with nearly the same true brightness, which lets you work out how far away it is by how faint it looks. By comparing the distances of these supernovae with how much their light had been redshifted, the teams could reconstruct the expansion history of the universe, how its growth rate had changed over billions of years. They expected to measure the rate of slowing. Instead, in 1998, they found the opposite. The expansion of the universe is not slowing down, it is speeding up. Something is pushing the universe apart, harder and harder, and that something accounts for about 70% of everything in the cosmos, and we do not know what it is. We call it dark energy, which is an honest name, because the word dark here means we are in the dark about it. The discovery of acceleration is worth lingering on, because of how completely it surprised the people who made it. The two teams, one led by Saul Perlmutter and the others by Brian Schmidt and Adam Rees, were not looking for acceleration. They fully expected to measure how much the expansion was slowing down, and the only real question, as far as anyone believed, was whether the universe contained enough matter to eventually halt the expansion and recollapse, or whether it would coast outward forever, gradually slowing. Both possibilities involved slowing. When the supernova data came in, the distant explosions were fainter than they should have been, meaning they were farther away than a slowing universe could place them, meaning the expansion had been speeding up rather than slowing down. The result was so unexpected that both teams spent a long time hunting for errors before they believed it. They had set out to weigh the universe's brakes and discovered instead that it has an accelerator pressed to the floor. The finding earned the Nobel Prize in 2011, and it remains one of the most profound mysteries in physics. What does the pushing is the thing we call dark energy, and the honesty of that name matters. Dark energy makes up about 70% of everything in the universe, more than the ordinary matter and the mysterious dark matter combined, and it behaves like a property of empty space itself, a faint pressure that comes with every cubic centimeter of vacuum and pushes outward. The more space there is, the more dark energy there is, and the more it pushes, which is why the expansion speeds up over time rather than slowing. As space grows, it manufactures more of the very thing that makes it grow faster. But what dark energy actually is, at a fundamental level, we do not know. It is the largest component of the universe, and the one we understand the least. We have named the 70% of reality that we cannot explain, and the name simply marks the size of our ignorance. It is also worth saying plainly that this changes the long-term fate of everything, not just the academic question of how big the universe will get. A universe that slows down and a universe that speeds up have completely different futures. A slowing universe draws more and more into view over time, knitting the cosmos together. An accelerating universe does the opposite. It isolates, it separates, it carries things apart faster and faster until they can no longer reach one another at all. We happen to be born into an accelerating universe, which means the future of the cosmos is one of increasing separation and isolation, of galaxies being driven apart and out of contact, and the gentle growth of the observable universe that we just celebrated is the early, temporary phase of a process whose later phase is loss. And acceleration changes everything about the future of the observable universe, because it means the second kind of growth does not continue forever. In a universe whose expansion is speeding up, the steady arrival of new light from beyond the horizon does not go on without limit. It slows and stops and reverses. The horizon stops creeping outward through the galaxies and begins instead to leave them behind. The universe getting larger in the way we just celebrated turns out to be a temporary phase, the behavior of a cosmos that has not yet felt the full force of its own acceleration. Underneath the headline that the universe keeps getting larger lies a quieter, darker truth, and it is time to face it. Because acceleration means that even as the universe grows, it is also beginning to take things away from us, one galaxy at a time, forever. Part 11. The universe is closing. Here is the turn, the hard one. Because the expansion of the universe is accelerating, there is a distance beyond which we will never receive any new signal, ever, no matter how long we wait. It is called the cosmic event horizon, and it sits at about 16 to 17 billion light-years away. The name is borrowed from black holes on purpose, because it works the same way. It is a line beyond which information can never reach you. Anything past the cosmic event horizon is emitting light right now that will never, in the entire infinite future of the universe, arrive at the Earth. The acceleration is carrying those regions away so relentlessly that their light, set out toward us today, loses the race forever. It will spend eternity falling behind the stretching of space, never gaining, never arriving. For everything beyond that line, this moment is the last contact we will ever have, and even this contact is only the old light still in transit, not anything happening there now. Now connect that to a single, devastating number. Of all the galaxies we can currently see in the observable universe, the overwhelming majority are already beyond the cosmic event horizon. By the standard analysis, something like 97% of the galaxies we can see tonight are already unreachable, not just in the sense that we could never travel to them, but in the sense that no signal we could ever send would arrive, and no signal they send after this point will ever reach us. We can still see them only because of light they emitted long ago, light that is still completing its journey, but the connection is already severed. If a civilization in one of those galaxies sent us a message today, it would never arrive. We are watching the light of 97% of the visible universe, the way you might watch a train that has already left the station and will never return, still visible down the track, already gone. The number itself, 97%, deserves to be felt rather than just noted. Of every 100 galaxies you can see, 97 are already beyond the point of no return, and only 3 remain, even in principle, within reach of a signal sent today. And that figure is not holding steady, it climbs. With every passing era, more galaxies cross the line. The 3 become 2. The reachable cosmos contracts toward our own small bound cluster. We are watching the most enormous thing that exists shrink in the only sense that matters for contact, slowly and silently and permanently. And the watching is not a forecast. It is a measurement of the sky as it is right now. Sit with what that means, because it is not a far future abstraction. It is the present condition of the sky above you. When you look at a long exposure image full of thousands of galaxies, almost every one of them is a galaxy we have already lost. The light arriving from them now is the last we will ever get. Everything they do from this moment onward is sealed off behind the horizon, beyond any possible knowledge. Their light reaching your eye is not an invitation to come closer. It is a farewell, already in progress, a goodbye that has been travelling toward us for billions of years, and that we are only now receiving. The night sky, the museum of preserved light, turns out to be full of departures. Most of what we can see, we are seeing for the last age in which it will be visible at all. And it gets quieter and more final from there, because the event horizon does not hold still. As the acceleration continues, the cosmic event horizon draws inward, in the sense that more and more galaxies cross outside it as the expansion sweeps them up. One by one, over the coming billions of years, the galaxies of the sky will redshift, dim, and slip beyond the horizon, their light stretching toward infinite faintness as they cross, until they wink out of view entirely. The universe we can see is, in this far longer sense, not growing at all. It is emptying. The expansion that made the cosmos larger than its age, the stretching we marveled at, is the same process now carrying the contents of the sky away from us, permanently, beyond recovery. The universe is getting larger and lonelier at the same time, opening and closing in the same breath. And the part of it we could ever touch or know is shrinking with every passing eon. Let me make the unreachability concrete, because the word can sound abstract. When we say a galaxy is unreachable, we do not only mean it is very far away, we mean that if, today, we launched a probe toward it at the absolute maximum speed allowed by physics, the speed of light itself, that probe would never arrive. Not in 1 trillion years. Not ever. The space between us and that galaxy is being created faster than light can cross it, so the gap grows faster than any traveller could close it, and the destination recedes forever ahead of the fastest possible pursuit. This is true for the overwhelming majority of the galaxies we can see. They are not merely far, they are sealed off, behind a barrier made not of distance, but of the relentless manufacture of new distance, and no conceivable technology can ever breach it, because the barrier is the structure of space itself. What this leaves us with, in the end, is a kind of cosmic island. The galaxies that are gravitationally bound to us, our own Milky Way, Andromeda, and the few dozen small galaxies of the local group, will stay with us. They are held together by gravity strongly enough to resist the expansion, and over the coming billions of years they will not drift apart, but instead fall together, merging into a single large galaxy. That merged galaxy is the entirety of what will remain reachable to us forever. Everything beyond it, the millions of galaxies in Laniakea, the billions beyond, the whole shining cosmic web, will recede, redshift, and vanish. The universe we could ever touch is not the 93 billion light-year sphere. It is one galaxy's worth of stars, our own little gravitational raft, adrift on an ocean that is carrying every other raft permanently out of sight. There is something almost unbearable about the timing of it, because the connection is being severed right now, in our era, not in some safely distant future. The galaxies are crossing the horizon continuously, and the light we receive from the ones already beyond it is the last we will ever get. We are living through the long goodbye, not watching it from the safety of before or after. Every long exposure of the sky is a photograph of a farewell already underway, of galaxies whose final light is reaching us even as their futures are sealed away. The night sky is not a stable possession. It is a slowly closing window, and we are looking through it while it is still open. There is no force we could ever apply to stop this. It is not a matter of building faster ships or better telescopes. The galaxies crossing the horizon are not moving away through space, where we might chase them. They are being carried off by the growth of space itself, faster than light, and nothing can be done about that, because nothing can outrun the expansion of the universe. The reachable cosmos, everything we could in principle ever visit, signal, or influence, is contracting toward our own small cluster of galaxies, and there is no version of the future in which that reverses. We are, slowly and gently and irreversibly, being marooned. And that marooning leads to a final vision, a picture of the far future, so strange and so sad that it forces us to reconsider how lucky we are to be alive right now, at this particular moment in the history of everything. That vision is where this journey ends. Part 12. The window we live in. Travel forward in time, far forward, 100 billion years and more, and stand on a world orbiting a star in the galaxy that the Milky Way and Andromeda will have long since become, fused together into a single enormous elliptical galaxy. Look up. The sky above this future world is black, and it is empty. There are stars, the local stars of the home galaxy, scattered overhead as always. But beyond them, there is nothing. No other galaxies. No faint smudges like Andromeda. No long exposure image, however long the exposure, would reveal a single galaxy beyond the edge of the home system, because every one of them will have crossed the cosmic event horizon, redshifted into invisibility, and vanished. The expansion will have carried the entire rest of the universe out of sight, and the sky will hold only the one merged galaxy and the surrounding dark. Now imagine the astronomers of that future world, and grant them everything: perfect instruments, brilliant minds, complete honesty, the full method of science applied without error. They look out at their black and empty sky, and they measure, and they reason, and they conclude, correctly given everything they can observe, that their galaxy is the entire universe, a single island of stars surrounded by infinite static darkness, eternal and unchanging. They will find no other galaxies because there are none to find. They will detect no expansion because the evidence for it, the receding galaxies, the redshift, will have long since disappeared beyond the horizon. They will find no cosmic microwave background because the relic glow will have been stretched and diluted into undetectability. Every piece of evidence that there was ever a Big Bang, that the universe was ever young, hot, dense, and expanding, will have been carried away. They will live in a universe whose history has been erased from the sky, and they will conclude, with perfect logic and perfect data, something that is completely false. They will believe they live in a static, eternal cosmos, and they will have no way whatsoever to know they are wrong. Let that turn back around on us, because it is the most important realization in this entire story. We are not those future astronomers. We are something far rarer. We happen to be alive in the narrow window of cosmic history when the evidence is still visible. The galaxies have not yet crossed the horizon. The microwave glow of the beginning still soaks through every room on Earth. The expansion is still measurable, written in the redshift of the supernovae. We can look up and actually read, in the light of the sky, the entire history of the universe, all the way back to 380,000 years after the beginning. There were no observers in the first billions of years to see this. There will be no observers in the far future able to see it. We arrived in the brief era when the truth is on display and the exhibit will not stay open forever. We are reading a book whose pages are being torn out one by one and carried off into the dark, and we happen to have arrived while there are still enough pages left to understand the story. This is not idle speculation. It is a conclusion that working cosmologists have drawn and published in plain terms. Two physicists, Lawrence Krauss and Robert Scherer, wrote a paper about this future with a title that says everything: The Return of a Static Universe and the End of Cosmology. Their point was exactly the one we have arrived at. A civilization arising in the far future, in the merged remnant galaxy, would have access to good science and would still reach false conclusions about the universe because the evidence will be gone. They would measure their own galaxy, find it stable and surrounded by darkness, detect no expansion and no relic radiation and no other galaxies, and conclude reasonably that the universe is a single static island of stars. Everything we now know about the Big Bang, the expansion, the age and history of the cosmos, would be not just unknown to them, but unknowable, erased from every observation they could possibly make. They would be doing careful science and getting the universe profoundly wrong, through no fault of their own. Turn that around, and the gratitude becomes almost overwhelming. We are not the future astronomers in the dark. We are the lucky ones, arrived in the readable era, when the galaxies are still visible, the relic glow still detectable, the expansion still written plainly, in the redshift of distant supernovae. The full history of the universe is still legible in the sky, and we happen to be here, equipped with the instruments and the curiosity to read it before the pages are carried away. There was no one to read it in the first billions of years, because there was no one yet. There will be no one able to read it in the far future, because the text will be gone. The window in which the universe is both inhabited and legible is narrow, and we are inside it. Of all the things to be grateful for, the sheer timing of our existence may be the strangest and the most profound. So return, one last time, to the number we started with, the number that should not be possible, 93 billion light years. When we first said it, it was a measure of how enormous the universe is, a triumphant headline, the full extent of everything we can see. But now, having made the whole journey, hear it differently. 93 billion light years is not only a measure of how much is out there, it is a measure of how much is leaving, how much light is still arriving from galaxies we have already lost, how much of the sky is a farewell still in transit. It is the size of the museum, yes, but it is also the size of the goodbye. The same number that once felt like a boast about how much the universe contains now reads like an inventory of what is on its way out the door, every light year of it full of galaxies whose connection to us has already, quietly, been cut. The triumph and the loss are the same measurement, read in two different lights. And the fact that we can still see all of it, still measure it, still understand it, while the future astronomers in their empty sky never will, is the rarest and most fragile gift the universe has given us. We are here while the lights are still on, and return, finally, to the phrase I asked you to carry from the very beginning. The edge is a moment, not a wall. We understand it completely now. The edge of the observable universe is not a barrier in space. It is a horizon in time, drawn around us by the age of the cosmos and the patience of light, and it moves, and it belongs to us, and it is different for every observer who ever lived. But there is one more layer to it now, the layer this whole journey has uncovered. The edge is a moment in two senses. It is a moment because it is made of time rather than distance, and it is a moment because the era in which we can see what lies near it is itself only a moment, a brief and passing window in the long life of the universe, and we are alive inside that window, looking out while there is still something to see. And let the very last image be a gentle one, because the universe, for all its enormity and all its leaving, is not unkind. The far future it is drifting toward is not a place of fire or violence, but of quiet, of patient cooling, of long and gradual rest. The galaxies do not crash to a halt, they simply slip away, softly, over spans of time so enormous that nothing about it is sudden. Stars will keep being born for a long while yet. Our own merged galaxy will shine for hundreds of billions of years. The closing of the universe, when it comes slowly, like a house settling into dark after everyone has gone to sleep, and there is something restful in that, something that does not ask to be feared. The cosmos is not ending tonight. It is only, very slowly, growing quiet, and we have arrived early enough to see it while it is still full of light. So let the climb end here, in the quiet. The universe is larger than its age should allow, because space itself has been stretching all along. It keeps getting larger, in the swelling of every distance and the slow arrival of ancient light. And it is, at the same time, beginning to close, carrying most of itself away beyond any horizon we could ever cross. All of this is true at once, and all of it is happening now, in the sky above you, in the faint warmth passing through the room, in the light of galaxies that left their farewell before the earth was formed. You are never looking at now. You are looking at the long, layered, departing past of the largest thing there is, and you happen to be here, awake, while it is still possible to look at all. Rest with that. The lights are still on, the museum is still open, and the whole receding universe is still, for a little while longer, ours to see.